Hi, everybody. This is Mr. Bing. It is November 11th, 2020 at 2:05 p.m. We are in room 409 at Liberty High School. This is Project Lead the Way Engineering Course 2, Principles of Engineering with Nathan and Lewis and Matt and John. And Nasim just walked out, but he is a valuable member of our little engineering team. And so anyway, I wanted to talk about this activity 2.1.7, especially since every time I tried to explain 2.1.6, it was a colossal failure filled with shame and embarrassment for me. But the students kind of reassured me that it's okay, that we all fail together. And so we remembered, actually, Nasim just reminded us before about if, when, will. If you fail, I fail. When you succeed, I succeed, and we will succeed together. And I'm hoping we will succeed. I'm hoping we will succeed together right now. So in this 2.1.7, calculating truss forces, basically it's about whether trusses can be solved, and if they can be solved, then you have to solve them. And so the first part here, I want to show you that to determine if a truss can be solved, you have to use this little equation. I don't know how well you can see that little equation. I'm just going to tell you what it says. 2 times j equals m plus r, and j is the number of joints. So when you look at this little figure, you get 1, 2, 3, 4 joints. So remember that j is the number of joints. M is the number of members, and that is 1, 2, 3, 4, 5 members. So m equals 5, remember that. And then the r is the reaction force from each of the supports or each of the mounts. And those here is shown a picture. This is a pinned support, and this is a roller support. And like I told you guys before, I'm not gonna, you can ask me exactly why this pin support has 2 reaction forces and that roller support has 1. Or you can just trust me for right now, a pinned has 2 and a roller has 1. So if you are counting the number of reactions, 2 plus 1 is 3, right? 2 plus 1 is 3. And then the number of members, if you remember the equation, m plus r, well, the r was 3 and the m was 5, or the m was 5, right? And so what is 5 plus 3? 5 plus 3? Uh-oh, I already made a mistake. I was looking at the explanation of the diagram, and I wasn't looking at the actual support system here. So let's start over. 4 pins, 1, 2, 3, 4 pins. 5 members, 1, 2, 3, 4, 5 members. And then this is a pin support with 2 resistance or 2 reaction forces. And this is a pinned connection with 2 resistance or reaction forces. 2 plus 2 is 4. So remember that part. The R is 4. The M is 5. 5 plus 4 is 9. Okay, that feels a little more comfortable to me. 5 plus 4 is 9. However, it has to equal 2 times J. And the joints, 1, 2, 3, 4. 2 times 4 is 8. And so we got 8 equals 9, which is false. And so therefore that truss cannot be solved. And I'll go ahead and give you a little bit of hint or a little bit of tip, or I'll just give you the answer actually. Number 2 is also false when you test it. Number 3 is also false when you test it. So all 3 of those are false according to the determinants equation 2j equals m plus r. You can look at those and figure out what the j's, m's, and r's are. Okay, then we get to this one. This one has a pinned support right there. That counts as 2 for the r's. This one's a roller. That counts as 1. So 2 plus 1 is 3. And then there are 1, 2, 3 members. So if you remember the equation, you got the m, which is 3, and the r, which is 3, which equals 6. And then you have to count the number of joints, which is 1, 2, 3. And according to the equation, you multiply that by 2, which is also 6. 6 equals 6 is true, which means that truss can be solved. And what do you know? They gave us a bunch of information to see if we could solve it. And so you can see the picture yourself, 3 by 3, ABC, 50-pound applied force, and there's a pinned support and a roller support. And so now let me show you my work. See, this is working, Nathan. So yes, it's working. And and I actually already have the work shown here. Oh, I can just point at my paper with a pen and my hand. Okay, so there's the 3 by 3, and there's the ABC, and there's the pin support and the roller support. That's how I draw a pin and a roller. And then the equation again, 2j equals m plus r, 2 times 3, there's 3 joints, 3 members, and 3 resistance forces, 6 equals 6, so it's true, it is solvable. It is solvable. Now, if you remember the original picture, they gave us a 50-pound applied force, but I don't think they gave us anything else besides those measurements 3 and 3. So I figured, looking at this roller, that there must be a force, one of the resistance or support or resultant. No, it's resistance, I think. One of the support forces. And so since this one is at A and it's in the X direction, I called that force A sub X. So you got A sub X, you got the 50. And then here at the B, there's two resistance forces or two support forces. And this one is the B force in the X direction. This is the B force in the Y direction. There's two of them, an X and a Y. There's only an X on the roller. So I also figured out, sort of accidentally, that if this is 3 and this is 3 by 3, and the diagonal is following that 3 by 3, that would have to be 45 degrees. And that will be relevant later, way down the solution. This is 2 full pages. All you can see at this point is 1/2 page. So let me see here. I've got the A sub X, B sub Y, and the 50. And a 45-degree angle that'll be relevant later. I tested the determinacy. It's called determinacy, and it is true. It can be solved. And so here I have the sum of the forces in the Y direction equals 0. This is one of the 3 equilibrium equations that everything has to equal out. All the forces have to equal and cancel each other out. And that's where we get 0 when they, that's when we get 0 when they're all equal and cancel out. So all of the forces in the Y direction, well, there is a B sub Y in the Y direction, and then there's a 50, which is the applied force in the Y direction. So if we take the B sub Y and add the 50, which is going to be equal to 0, but then it occurred to me, and I almost missed it. See that, John? I almost missed it, that it's a negative 50 here, because that 50 is down on the XY coordinate plane, traditionally down to be a negative. That B sub Y, therefore, is going to be positive when you solve this. B sub Y equals 50. And rather than say positive, I just gave it an up arrow to sort of remind myself that B sub Y is indeed up. And the 50 is down. I mean, obviously you can see that. Okay, then I had to figure out the sum of the forces in the X direction, or I know the sum is going to be 0. So I had to figure out what this A sub X and this B sub X, those are the only 2 X forces that I have. And I know they have to cancel each other out. And I already see that there's a problem. Don't panic, Lewis. Don't panic. I see that there's a problem, but I knew it from the beginning that this A sub X and this B sub X cannot be both in the same direction. One of them is reversed. And when you look at the sum of the forces in the X direction equals to 0, well, I take the X force, which is A sub X, and I take another X force, which is B sub X. I add them together and I get 0. You can't add 2 positive numbers and get 0. So one of them has to be negative. And just arbitrarily, I said the A sub X is equal to the negative B sub X. They must be in opposite directions. Okay. This is sort of working a little bit. Let me move that out of the way. That was strange. Okay, now I'm going to slide up the page and just remember everything that was up there above. So now I have the sum of the moments, In physics class, we call it torque, but or moment of inertia, maybe. But in engineering, we call it a moment. The sum of the moments is equal to 0, just like the sum of the X forces is equal to 0 and the sum of the Y forces is equal to 0. And when you're calculating moment, you have to determine what your relative point is. And you can choose anywhere, but there's some that are more convenient than others. I chose my relative point to be B, because whatever point you choose, any forces that are applied at that point get automatically canceled. Mr. Tone just walked by, everyone. Yes, Mr. Tone. Yes, indeed. And here he has arrived. Come on in, Mr. Tone. Let me pause my recording. Resume. I think I've resumed recording. And so I don't exactly remember where we were before Mr. Tone walked in, a good friend of mine, AP English teacher. He loves The Great Gatsby and the Beatles. So when we left off, I think I was talking about moments. Is that what I was talking about, guys? Okay, the moments. So all the moments have to add up to be 0. Well, they have to sum to be 0. Now, what a moment is the force multiplied by the distance to the pivot point, or not pivot, but the point of rotation or potential rotation, or the relative point that I've chosen, which I chose point B. And so for the moment that is caused by A sub X is going to be the value of A sub X multiplied by the distance, which is going to be 3. And then the value of the 50 applied force is going to be 50 times the distance. And I know you're looking at this thinking it's a diagonal distance, but we measure it from the perpendicular of that vector, which is straight vertical. So we measure it across here. So the distance for that 50 is also 3. So we get a sub x is equal to 3. I'm sorry, a sub x multiplied by 3, and we get 50 multiplied by 3, and they have to add up and equal 0. So I hope you can see that they both can't be positive in that scenario. Something I know about the a sub x force when it comes to rotation is if I'm using B as my pivot point, then the rotation here, if you follow that, and don't worry, it's not actually rotating, but the a sub x is trying to make it rotate, and that direction of rotation is counterclockwise. Counterclockwise turns out to be positive, and that's what I have here. I don't know how well written that is. CCW, counterclockwise, is positive. And then this C force that's pulling down, if it's relative to the B point, then it's trying to rotate in this direction, which is clockwise, and for some inexplicable reason, clockwise is negative. I actually do know the reason. I'll explain it to you if you ever want to know. So then clockwise would be negative. That's supposed to be a little CW. So I got 3 times a sub x. Remember, that's a 3. A sub x is unknown. I've got 50 times 3, which is 150. However, it's negative. And then when you solve this equation, you get 3 a sub x equals 150 with the inverse operation. And then you get a sub x equals 50 with the inverse operation. And remember from above, I said a sub x and b sub x have to be equal and opposite. One of them has to be negative. Well, if a sub x is 50, then b sub x has to be negative 50. And notice that I did not put a negative sign there. I wrote down here, little tiny, negative equals left. So this force is 50 to the right. This force is 50 to the left. So back in the original picture here, it looks like my b sub x is backwards, and I knew one of them would be, and we will address that a little bit later. Okay, so based on what we have so far, I can redraw my truss with the 3 points, A, B, and C. And I'm just going to have to remember that that was 3, and that was 3, and that was 45 degrees. I know that there's an applied force that is down 50, and I know there is an A support force in the x direction, which is to the right, 50, and I know there's a B sub x support force that is to the left, 50, and then I know that there's a B sub y force that's to the up, 50, which is kind of nice. Notice that I have an error here. I kind of got off the track when I was drawing that line. So these little X's mean that to ignore that line. Moving on. That's only half of the problem. Everything I've said so far for the past 30 minutes is only half of the problem. So next is going to be what's going on at each individual point. At point A, there is an A sub x force being applied to the right. Well, here it is. At the A point, there's an A sub x force being applied to the right. Now, you cannot have a force existing in isolation. No force may exist alone. It has to have an equal and opposite partner. And so this A sub x equals 50. There's another force to the left that's equal to 50. However, this one is called A sub c sub x. And where did that come from? That is the force on point A from point C. So this one actually applies a force through the member onto the other one. And that's what this A C sub x is, the force on A from C in the x direction. It has to be equal and opposite of the only other horizontal force. And so they are both 50, one to the right, one to the left. Now this one is the force acting on point A from point B. And we notice it's in the vertical direction. That's right here. The force on A from B in the vertical direction, which is sub y, equals 0. Now, how did I know it was 0? Because there's only one force there. And remember I said just a moment ago that you cannot have one force. You must have an equal and opposite force. There was no other force, so it actually doesn't even exist. I've drawn it there, and the value of that is 0. Okay, point A has been completed. We have the overall truss, which we did, and we have point A now, which we did. And remember, this is like a Sudoku, which means whatever happens at point A is going to affect point B and affect point C. And so now I have turned to the page, just like, who's that? Bob Seger, turned the page. Wonderful, wonderful song. Point B now, I have to do an analysis of that point. And remember, I had a vertical B sub y, the support force of 50, and I had a horizontal B sub x, support force of 50. And now this B sub a sub y, well, actually, remember it was AB sub y because it was the force on A from B. Well, it's the same force on B from A. It's an equal and opposite force from the other member. Trust me. BA, the force on B from Y, the force on B from A in the Y direction, and it was 0 in the A point, and it has to be 0 on this B point as well. So that force, even though we've drawn it there, does not really exist. Then we have this thing. This is BC. Where does BC come from? BC comes from this solution that we had. It's the force on B from C. It's Sudoku, everyone. What happens at one affects the other. The force on B from C. And so I don't know what that is. And so when I drew this originally, I just labeled it BC. And I didn't know that it was 70.7. Oh my gosh, we have 5 minutes. So I didn't know that it was 70.7. But what I do know is that it's a 45-degree angle. And that 45-degree angle is going to have a horizontal component and a vertical component. I don't know anything about the horizontal component except that it is equal and opposite to this B sub x, which makes it 50. I wrote down a little 50 there. And then I don't know anything about this vertical component except that there is an equal and opposite over here, which is 50. Remember, this one is 0, doesn't really exist. And all of this really makes sense because if this is a 45-degree angle, then the legs have to be equal, 50 and 50. And using the Pythagorean theorem, just trust me, the Pythagorean theorem, 50 squared plus 50 squared, and whatever the sum of those are, square rooted, gives you 70.7. Now we're done with point B. Well, let's look at point C. It is being affected by the other points. Remember, there was a point on A from C? Well, there's an equal opposite force on C from A. And trust me, on the other side of this page, it says that the AC sub x is 50. So that means the CA sub x is also 50, but they're equal and opposite directions. The one on the A point was to the left, so the one on the C point is to the right. Then we have the applied force. Remember the original applied force of 50? Well, it's there. But then this diagonal force. Remember there was a diagonal member from B to C. Well, that diagonal member still exists from C to B. And there is a force on C from B. And we already know it's Sudoku. We already knew that BC was 70.7. So that means CB has to be 70.7. And they have to be equal and opposite. So we put all this together to have a final Sudoku solution. A final Sudoku solution, the final solution, that sounds really wrong. But the final solution, you got point B, you got point A, you got point C. Point B has a 50 to the left, a 50 to the up, a 0 to the down, and a 70.7 to the diagonal. Point A has a 50 to the left, a 50 to the right, and a 0 to the up. So these don't really even exist at all. And then at point C, we've got a 50 to the right and a 50 to the down and a 70.7 that diagonal. I mislabeled this before, so that's why that's crossed out. A sub C sub x is to the left, A sub x is to the right. Then to really clean this up, this is it, Nathan. Notice it's got a box around it and it's got a big check mark indicating that that is the solution and it is correct. Point B with the forces acting on it, point A with the forces acting on it, point C with the forces acting on it. We know what all of the values are for all of those forces. So for the first time ever, we can celebrate the fact that we have correctly and completely solved a truss problem. Yes, 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 everyone. Yes, yes, yes. So thank you so much. I finally feel good. It's nice to finally feel something positive. And I'm going to stop or pause the recording and say bye-bye, everyone. Have a wonderful day and weekend and whatever else you have coming up in your life.